matter, but if I was asked to bet on it, I would say I'm not yet confident the signal is real, that we will discuss, and we will get to the details in a few minutes. Lincoln Greenhill will describe the observational results that came out in Nature yesterday on detection of hydrogen from the cosmic dawn. And then Julian Munoz from the physics department will tell us about the limits on dark matter baryon interactions and the possible connection to the signal that was reported. And then we'll hear from Volker Springel that will tell us about cosmic rays in galaxy formation simulations. And after that, we'll hear from the CFA colloquium speaker today, Laura Kreidberg, that will tell us about not cosmology this time, but something closer to home: water, methane, depletion, and high-altitude condensates in the atmosphere of the warm Super-Neptune WASP 107b. And finally, we'll hear from a visitor, Alex Lazarian, that many of us know very well. He's over there, visiting from the University of Wisconsin, and he will talk about 3D distribution of magnetic fields in molecular clouds. We'll start with Lincoln. Article on this detection.
So hopefully good. The microphone has not been destroyed when I dropped it. Thank you, Avi. And I guess that is... Okay, pardon me. So thank you, Avi, for mentioning the importance of inspecting this reported claim in the literature. The experiment's name is EDGES, that you'll find in the Nature paper. So EDGES on the edge is just my wordplay as I try to come up with ever increasingly clever ways of presenting the result. This is taken from the News and Views. This tortured axis of tick marks and seemingly irregularly spaced numbers is motivated by redshift, but the important thing is what's shown in black is the radiation temperature from the cosmic microwave background, which is cooling with expansion of the universe. And then let's ignore the red, just the blue curves. I can use modern technology. So the blue curve is the gas temperature, and that cools more quickly than radiation temperature. And what is shown in this wavy solid blue line, again ignoring the red, is the spin temperature of hydrogen in the 21 centimeter ground state transition. And that varies between these two temperature reservoirs based on, for instance, how strongly collisionally coupled it is, or in this epoch, which is poetically referred to as cosmic dawn, it is coupled to the gas temperature because of ultraviolet and the Wouthausen field effect, that is, Lyman alpha coupling from the first stars. So this is a refrigeration, but just of that transition. The important thing is that if there weren't that ultraviolet emission, there would be no signal that we could detect at this epoch. So it's simply the stars provide the trigger, and after that we have a tracer. Of course, the gas temperature is the gas temperature irrespective of whether we have that coupling. Now, the red curves. The measurement that's reported in, and which I'll be showing in the next slide or two, suggests that the gas temperature is colder than it should be with just adiabatic expansion or adiabatic cooling and expansion, cosmological expansion. That's what this dashed blue curve is. So this is now the artistic demonstration of we had colder gas temperature, and instead of being around 10 degrees, it's around 5 degrees at a redshift of 20 or 180 million years after the Big Bang. So what that means is when the stars turn on, instead of seeing something that maybe bottoms out at this temperature, we actually have coupling to a much colder reservoir, and that's what is detectable in 21 centimeter at high redshift. This is a picture, even though there's a plastic drink bottle on the top, which is the extremely high-tech way to protect your sensitive electronics that this group used. This is essentially just two square panels, and it makes up a dipole antenna. And they choose the specific geometry to obtain some optimizations in terms of what the gain pattern is of the antenna across the sky in different directions, how sensitive they are to the horizon. There's a lot of thought and meticulous design that goes into all of the details here. But otherwise, we see an Australian landscape and a lot of mesh shielding on the ground, which is intended to isolate the antenna both from the horizon and from the soil, because at wavelengths of meters, you're actually seeing down into the soil. It's not just a matter of things zooming across the surface. Okay, so the EDGES experiment sees a temperature of the sky, which is shown here. Frequency is on the x-axis, so this is TV, this is TV and radio, and the sky is very hot. It's thousands of degrees. Shown then in the next few panels are models and residuals, and the important model, most important model in this figure is shown here, D. This is the thing that is either troubling or exciting, depending upon how you look at it. Specifically, this is an indication. This is a flat-bottomed curve with an amplitude of minus 1/2 degree K, absorption against the CMB. That is not predicted by any mainstream model. All the mainstream models had things that look like inverted Gaussians, nothing that's flat-bottomed, and the absolute maximum amplitude that could be generated was about 200 milli-K. So this is 2 to 3 times too deep, and it's the wrong shape. The team was very careful in that they kept perturbing their experimental apparatus and their data analysis technique over and over in order to see if they could generate a different line profile. And they couldn't. Within the parameters that they found they could vary, they just kept coming up with the same thing, and that boosted their confidence. However, this is in some sense limited by imagination and how much time you have and how many supplies you have and whether you can afford to rebuild your experiment from scratch, changing everything. So that's in fact what is important to do now in the community, and there are two groups. We have one which are going to run crash programs to try to duplicate this result. But so they run many replication tests. The question is, were they broad enough? And some of the things that I won't go into in detail are just things that you might focus on, which were not dealt with by that team. For instance, they have an electronic simulator of the antenna, so that when they're in the lab, where you can't set up an antenna and have it perform as if it's in the desert because of the walls and the RFI, you just set up some piece of electronics, you plug it into the receiver, you demonstrate that it works well, and if the simulator is accurate and well calibrated, this works. Well, maybe the simulator needed some more variation, or it needed to be kicked a little bit more. And then there are a few other things. One that is actually circulating this morning has to do with methodology of how they were fitting their data, using a linearization versus nonlinear. James has been thinking about this, Daniel as well. Maybe they'll say some words later. But I think that the last thing I want to note before Julian's talk is the importance of this red curve and the fact that the temperature is lower than it could be from astrophysics only. And one of the answers, which Renan Barkana writes about in the same volume of Nature, is what if it's simply dark matter? That is, the dark matter is colder than the gas, and what if we have some amount of transfer, perhaps due to scattering, between these two things? And of course, dark matter should not do that, and that's why this is potentially revolutionary if it's confirmed. Thank you. Right. And in fact, it's whether it's the foregrounds or the fine points of the instrument, all of that is a matter of, okay, I believe I understand my instrument or my foregrounds, but how do I know that there's not actually a wiggle that's real somewhere in some component or somewhere in the synchrotron background that I haven't modeled adequately at a part in 10 to the 5 or 10 to the 4. Yeah. Yes, right. Hopefully we don't all make the same mistakes. Yeah, Erwin.
Did I understand you correctly that your hospital, it's been postulated that dark matter was interacting with regular matter in a way that's not expected? But why would that type of interaction be confined to the early times? That would be discussing the
Yes, that's for Julian's talk. Thank you. Giovanni.
Can anybody repeat this experiment soon? Or?
I can't define soon. I hope so. I think that we're on a reasonable track to have to replicate it by the middle of May. That is, we'll have all of our data collected by the end of April, and we have, I shouldn't say stand-in data because it's real data. We have data from last spring, which we'll use before that in order to perfect, in quotes, our analysis technique. The fact that we're now looking for something that's perhaps 5 times stronger than we thought in our most optimistic dreams is good, but you know, every instrument has its defects, and we're going to be focusing on those.
So you're talking about
LIDA, right, the LIDA project.
SARAS.
Right.
What's the quality of their data?
So SARAS, I've only seen a couple presentations of SARAS data. Basically, oh, sorry. There's a, so we all have idiotic acronyms. So ours is standing for Large Aperture Experiment to Detect the Dark Age. SARAS stands for something that's chosen by Ravi Subramanian at Raman Institute. In terms of it's like EDGES, it's an antenna. They put it out in an isolated location with lots of calibrations and well understood receivers, and then they try to extract this signal in the midst of all of this very bright foreground and ionospheric emission as well. So there are 2 projects that have been attempting to make this, 3 that have been attempting to make this detection in this Z of 20 redshift range, and one is EDGES, then we have ours, and then we have SARAS. SARAS has a better site than we do. In the Himalayas, they found a place with no FM to speak of. And we work at the Owens Valley Radio Observatory, where we're shielded by a lot of mountains, but still we have FM radio because it's California.
But SARAS is not optimized in the low frequency range, right?
What's that?
SARAS is not built for low frequency.
SARAS, so the initial SARAS experiment targeted the epoch of reionization. Thank you, Anastasia. And then they realized that they had a really good observing system, so they started observing a very broad band, including this low frequency section around 70 megahertz. And I haven't seen any results from that. They've only presented their epoch of reionization results, which are a flat spectrum obtained via, well, it's written up in a 2017 paper, so I wouldn't go into detail and take time on that. So,
Potentially, if you know what the signal is claimed to be, it's easier to read.
right, yes, definitely. So I think, especially because there are no other tracers that we can cross-correlate with, actually having reliable predictions from simulations so that we can do a proper filtering of the data, that could be what's critical, and then most critical about in being able to include dark matter models. Okay, thanks.
All right. Cool. Thank you, Lincoln. So I'm Julian, and I'm going to be telling you about work I've been doing with Avi on the dark matter implications of this measurement. This measurement is really exciting by itself. This is 21 centimeters from cosmological distances, but if it can also tell us something about dark matter, it would even be better. So let me start with telling you, like Lincoln mentioned, that 21 centimeter temperature is twice as deep as you would expect. That's great for detection, but this is hard for us theorists to explain. Since during this era, the 21 centimeter temperature is inversely proportional to the hydrogen temperature. So you need the hydrogen to be twice as cool as you would naively expect. To understand why this is puzzling, let me give you a quick rundown of the thermal history of hydrogen. After recombination, hydrogen is still coupled thermally to photons, since there's a small amount of free electrons left. About redshift 200, it starts decoupling and then just cools down adiabatically toward redshift 17, where the edges data lies. Temperature should be about 8 Kelvin. They measure it to be 4 Kelvin or lower. And this is not something you can do with astrophysics, since that would just heat up the gas, or you produce poor Lyman alpha coupling, which goes the other way. And if you want to change this decoupling, you will have to change recombination, which we understand fairly well from the CMB. An alternative is just you cool down the baryons by coupling them to dark matter, which is a cold fluid. This is not a fairly new idea. To cool down the baryons by a factor of 2, you need at least as many dark matter particles as you have baryons, since by equipartition you have to take away half the energy. And answering Irwin's question, you need the cross-section to grow at later times instead of early times. So if it goes as some steep inverse power law of velocity, dark matter would tend to couple thermally later instead of early. So you achieve that with some v to the -4 scaling, something like Rutherford scaling. For this, there's two kind of dark matter models that can give you this. One of them is a new dark matter interaction, something I've worked on in the past. Just say I couple my dark matter and my baryons with a very light field. And this light field is like a photon-ish. And this gives you these interactions. This is what Renan Barkana has written in Nature. This, however, this new field could also be produced in stellar environments like red giants, and could also act as a fifth force. So it's actually strongly constrained. So when Avi and I were looking at this, we realized that there's a second option, which is you charge the dark matter a little bit under the usual E&M force, in which case the regular photon doesn't have to mix with the dark photon, and you're fine. So I'm going to talk about this case. In this case, the entirety of dark matter cannot be mini-charged, and this is because we know that it's a cold collisionless fluid, mostly. So when you have a cluster collision, for instance, we know the dark matter, in blue, stays ahead of the baryons. If dark matter had a charge, it will get trapped in shocks and not be able to stay ahead. However, as much as like a few percent, 10% of the dark matter could be charged and still be consistent with all this. And that's what you would expect if dark matter was forming some sort of neutral state, like a bound atom, like a dark atom, but it's not necessary. So in this case, there's still constraints. So this is the plot of dark matter charge in units of the electron charge versus its mass in MeV. And these are constraints from supernova 97A, since we know it cooled mostly through neutrinos, not through milli-charged particles, because we see the neutrinos. From BBN, since if these particles are lighter than the electron mass, they would act as ineffective slight degrees of freedom in BBN. From the Slack milli-charged experiment in brown. And in purple, if you have a dark photon, the dark photon can itself be a degree of freedom in BBN. So you can also get a constraint. Now, the lines that you need to cool down the baryons by a factor of 2 are these for different fractions of dark matter, from 10%, 1%, etc. Notice that they all have a constant charge to mass ratio, which is what you would expect from E&M interactions. It's a charge to mass ratio what matters. And each line ends as at 6 GeV times FDM, since that tells you how many particles you need. You need dark matter to be light to have enough particles by equipartition to lower the baryon temperature. So it's possible that we have seen dark matter. It's possible that it's a small fraction of the dark matter. Seems to be the only way to make this work. And if so, this will give us a new window into dark sector, since these particles interact fairly strongly with us. So you will be able to access the rest of the dark matter through these guys. So I'm gonna leave you with a picture of there's a 21 centimeter temperature as a function of redshift with no X-ray heating and full Lyman alpha coupling. So this will give you the lowest absorption you can have in 21 centimeter. And the green line is lambda CDM. And as Lincoln mentioned, it doesn't quite get to the edges data. which, by the way, the error bar here could go lower, but it cannot go any higher. This is 3 sigma. When you add the interactions with just 1% of the dark matter, some millionth of the electron charged dark matter, you can actually explain this data. So that's it. Thank you.
And the reason it's difficult to do the experiment in the laboratory is because the one will lead to the form of the dependence.
That's right. So if you look at the accelerator constraint, there's only one from SLAC, and it actually ends at 100 MeV. There's a proposed LHC experiment, not even built yet, that will constrain millicharge, so 10 to the minus 3, so all the way up in this plot. And that's not even constructed yet. So this is very hard to probe with standard particle physics accelerators. That's why astrophysics is one of the best ways to detect these particles.
Cosmic dawn was the time when the baryons were the coldest ever.
That's right.
That's the reason.
Yeah.
Questions? Sorry.
Isn't the Z of the detection also at an unexpected place? I thought that from Planck measurements, and Thomson scattering of the CMB photons per nature galactic implied 8 or 9.
Well, that's a good question. So you would, if reionization happened instantaneously, yeah, it's redshift 11 or below, but we don't expect it to happen instantaneously. And actually people in the physics department are working in cosmology on whether there could be some early sources of reionization. So you wouldn't might not reionize the whole universe. Also notice this is X-ray heating, what will happen after. So you have,
Two different things.
Yeah.
The optical depth from has to do with free electrons. That's when hydrogen got ionized. Before hydrogen got ionized, it was heated by X-rays. But it was not ionized. The X-rays just deposited, they did some local ionizations, but eventually that internalized. And so the gas was, the intergalactic medium was heated without being ionized. And that's what allows you to see absorption. But otherwise, if you don't have hydrogen, you don't see absorption.
Just quickly, does charged dark matter have any implications for the direct detection experiment?
it's a good question. So so the cross section that you need for the V to the minus 4 is actually rather large. So if you just make the whole dark matter interact with baryons, without forgetting about charge or anything, you have a cross section of 10 to minus 30 centimeters squared. That would be strongly constrained by all direct detection, unless you somehow have shielding from the atmosphere, shielding from the ground, but they still interact very strongly. As I mentioned, mini-charged particles interact with magnetic fields. And we know there's supernova shocks in our galaxy that could, in principle, eject these particles. And you would expect them to be ejected and not cool down efficiently like our side, like the baryons. If that's the case, they could get out of the disk, and the magnetic field of the Milky Way wouldn't let them re-enter. So you would have a fraction of the dark matter that is charged that would be outside the disk, but most of the dark matter in the disk would be neutral. So you might not actually see anything in direct detection.
Or maybe Earth's magnetosphere keeps it all out.
We actually talk about it in the paper, yeah. It could act as, it could scatter with the atmosphere, have like a sort of like aurora borealis, if it scatters strongly enough.
Potentially, simulations like Volker Springel was presenting today, they introduced the physics of mini charged dark matter, and perhaps there will be some phenomena.
Yeah.
Any other questions for Julian? Just one point of clarification, because people may not have the full picture, is the hydrogen cools adiabatically faster than the cosmic microwave background. That's why it's cooler.
Right.
And then it heats up due to X-ray heating, and that's what terminates the absorption flow. And then once the hydrogen is above the microwave background temperature, it appears in emission, and that's when the reionization bubbles start to form and they overlap.
So yeah, so
It depends on the model, the sources. People often calibrate it based on X-ray binaries that we have locally. So per star formation rate, you can infer how many X-ray binaries are formed and how much X-ray is being produced. So around redshift between 10 and 20, that's where the heating takes place. I should mention that the stars are also important, not just the X-rays, because the stars produce Lyman alpha photons or ultraviolet photons, and those are important to keep the spin temperature coupled to the kinetic temperature of the gas, because the collisions among the gas particles are not frequent enough to keep the spin temperature at the gas temperature. And so the gas gets to the microwave vacuum temperature before before the first stars form, and it sits there. There is no contrast between the spin temperature and the microwave, so you wouldn't see the gas in absorption unless there was ultraviolet radiation produced by the first stars that couples the spin temperature to the gas kinetic energy. So there are two phases here: UV production, allowing the cold gas to appear in absorption, and then X-ray heating that terminates the absorption. However, all theoretical models, including those that are non-conventional, like Julian was describing, have a V shape for the absorption. And the V shape results from the fact that you have cooling that is followed by heating. So two trends that intersect, and you end up with a V-shaped absorption profile. The claimed observation is of a U-shaped profile with a flat bottom. That is very difficult to produce physically. That's why I am still quite nervous about the validity of this result. Because in order to produce a flat bottom, what you need is to balance delicately heating and cooling for an extended period of time such that you maintain a balance between the two. That requires fine-tuning. That's really difficult. None of the models that exist in the literature, including non-conventional ones, will produce you a flat bottom. So that's why this is, the result. Observations make sense only if there is a theoretical framework to understand that.
Spoken like a true theorist.
So I recognize that we're spending more time on this than we should, but the key feature of this is that the dark matter temperature, kinetic temperature, is lower than the gas temperature. It decouples with the earlier.
Right.
But it will decouple later if it's got a charge.
Oh no, because of the one with
So you actually it was never coupled originally. It was produced thermally. It was produced thermally, adiabatically cooled very fast, and then it was basically zero temperature-ish for a long time until it recouples. So most WIMP models actually don't have this feature because their velocity, the cross-section is usually velocity independent. So then they couple early on and they decouple. Here you have the opposite.
But the good news is even if the result, the observational result turns out to be scrutinized in the future, it can be used to put limits on the charge of the dark matter. Thank you very much.
Thank you.
No, I don't this. Okay, there we go. Yeah, thanks. I just want to briefly motivate why we are thinking about additional physics in our cosmological simulation of galaxy formation, namely magnetic fields and cosmic rays lately. So what we are able to do these days is from cosmological initial conditions at high redshift, initialized in lambda CDM, looking at 10 to the 12 solar mass dark matter halos, running this forward in time with a hydrocode, we're getting spiral galaxies that look at the end like this. So relatively nice disk systems, and they have the right sizes and the right stellar mass. They're also fairly thin. Here's a basic distribution of their kinematic structure. You see here the disk component, which is centrifugally supported, and a small bulge. So finally, these hydro simulations are able to produce disk-dominated galaxies that are looking very much like late-time spiral systems. This has been a holy grail for a long time, and us and several other groups are able now to do this. And here, just to show you how successful these are, they really lie in the blue cloud. Here's the Milky Way galaxy, and these systems cluster around the Milky Way in the plane here of stellar mass and star formation rate. So they are now having low enough stellar mass, which was always a challenge, but also still some star formation rate consistent with today's galaxy. So that's a nice success. You can also do, just as a parenthetical remark, making some interesting predictions. For example, here is a correlation between the recent mass growth in the black hole, the central black hole in these galaxies here in the vertical axis versus the disk radius. And you see, interestingly, that there's an anti-correlation. So this suggests that at least either the smaller disks are somehow truncated, prevented in growth here by the black hole if it's growing a lot, or some other cause like this. So this is one interesting prediction we got out of this. But what I really want to talk today briefly about is sort of the need to add physics that's not or wasn't previously in the calculations, but is clearly relevant for the interstellar medium, namely magnetic fields and cosmic rays. So we have added ideal magnetohydrodynamics to our moving mesh code. This is more complicated in this case because of this changing topology of our moving mesh. And we need to fulfill the divergence B constraints, or I don't want to bother you now with technicalities, but it cost us some work to eventually get this working. And so we can repeat these disk simulations with magnetic fields included, and we start with, for lack of a better scenario, with a tiny homogeneous field of 10 to the minus 14 Gauss or so, then look at the amplification of this field in these galaxies. And what we interestingly find is that already at very high redshift, this is really at early times, this is look-back time here, 13.5 gigayears. So in the first proto-galaxies that form, that later develop into these spiral galaxies, we have already an exponential amplification of the magnetic field in the centers of these galaxies. And we think that this happens on several hundred mega-years timescale, and then the field saturates at fractions of a microgauss or at microgauss levels when basically the pressure forces start competing with the thermal pressure forces. And we think that this is basically a signature of a small-scale dynamo that we begin to resolve in these systems. Here you see at high redshift the gas flows and the velocity field into these objects, and in the centers we have a highly turbulent flow. We can measure the power spectrum of this turbulence and also the magnetic field power spectrum. And the change in time here is basically consistent with the signatures expected for a small-scale dynamo, which has the ability to really amplify these fields on exponential and short time scales early on. In fact, we are certain if this is really a small-scale dynamo, we under-resolve it quite significantly. So if we had better resolution, the amplification would happen still faster. It would saturate at the same final field strength, though. And this final field strength, this is a radial profile of the magnetic field. Now in these disk galaxies, here in microgauss versus radius, the blue lines here are simulated systems, and these are two observational results, one for M101, and these are other spiral galaxies, a sample from Bars and Roy with rotation measures. And you see that these profiles are kind of consistent with what we observe. This is also sort of expected, of course, because we really have fields that are close to equipartition at the end, and if the thermal pressure is roughly okay, we expect to lie there. Now, magnetic fields, they also produce buoyance forces, and if you have just magnetic fields, you occasionally get little tiny fountain flows that reach heights of a few kiloparsec above the disk, sort of a Parker-like instability, but it becomes only really interesting if you add the other crucial component. Once you have magnetic fields, you should then also consider cosmic ray pressure, which in our galaxy is another contribution at equipartition with thermal and magnetic fields. And cosmic rays now propagate along the magnetic field, so we'd like to simulate this as well. And we have at the moment a very simple two-fluid model of basic thermal gas and a cosmic ray fluid that's coupled through this hyperbolic system through the ordinary ideal MHD. And then you have interesting energy exchanges between the cosmic ray component and the thermal gas. You also have transport processes that you need to model somehow, how the cosmic rays now move relative to the magnetic fields. And here we use, for example, a simple anisotropic diffusion term here, where the gradient in cosmic ray energy is dotted into the direction of the B field. So that means basically you have a diffusion process with a galactic diffusion coefficient that we take from the observations along the magnetic field. And just to tell you that this numerically is not entirely trivial to do this anisotropic diffusion, just to highlight this sort of generic problem. Imagine you have in a grid code some situation where you have a hot cell and a cold cell. This now refers to basically thermal conduction, where you have exactly the same type of problem. And here, when you have these two cells at an interface, you would now, for example, compute some negative temperature gradient. So, for example, in this direction, this would be, say, expected. But if you now dot this magnetic this gradient into the direction of the B field, which is indicated by this other sloped line here, you make basically a scalar product, you dot it in here, and you see that you get a flux now in the opposite direction relative to the phase, the so-called entropy violating flux. So simulating things like anisotropic diffusion is actually hellishly complicated, and it took us a long time to get this working. So we have actually now two codes that do that, and I spare you the details, show you some results now. if you apply this anisotropic diffusion to a coupled cosmic ray thermal energy fluid and do star formation in a disk galaxy, you get suddenly some very interesting dynamics in the gas. You see cosmic ray-driven winds, and this is basically, if you concentrate on the lower panels here, shown in the velocity field, that's shown here in these diagrams. And the color up here is, color code is basically the vertical velocity, and the disk is seen edge on here. Is here in the velocities are small, but above and below the disk there's a positive and negative strong wind blown by the cosmic ray dynamics. This wind is entirely absent if you lock the cosmic rays into the gas. If you do not allow for diffusion, then you just puff up the disk and you create these little fountain flows that fall back immediately. So the dynamics, and that's a well-known thing in theory, of course, is that the particular properties of cosmic rays, that they have a relativistic equation of state differently from the gas. It means, for example, that if you have a composite of thermal gas and cosmic rays and you move that composite to lower densities in an outflow, then the cosmic ray pressure decays slower way than the thermal pressure. So you become quickly cosmic ray dominated. And in the halo, you will then set up a more or less gradual cosmic ray pressure gradient, which can sustain this sort of outflow for a long time. And since in galaxy formation we're desperately looking for the physics that causes galactic winds and outflows, that suggests that this cosmic rays might be a part of the equation. So we've started to look into how this effect varies with halo mass, and also here, interestingly, so these are different disk galaxies of different halo mass. You find here a very strong variation of this effect that has to do also with the cooling properties of the systems with halo mass. And interestingly, then you can look at the mass loading of the winds, how they change, how this changes as a function of virial mass, and also the energy loading. So basically, how much of the cosmic ray energy, which is here produced by the supernova remnants, is actually appearing as kinetic energy flux in the wind. And what's interesting is that this energy loading efficiency is flat. It doesn't change with virial mass. This is the standard assumption also made in more simplified treatments of galaxy formation simulations, that the winds basically tap with a constant efficiency into the energy budget of the supernovae. So that is actually recovered here. And then the variation of the mass loading with mass, which you see as is very steep, changes very rapidly, actually more rapidly in our simulation models than in the observations here by Heckman and Chisholm. That means that this cosmic ray effect will be very strong in dwarf galaxies, but maybe too weak in the bigger systems here. What we're still working on is to figure out, unfortunately these treatments depend to some extent on plasma physics details. For example, what the cosmic ray injection efficiency is, and also what the diffusion coefficient is, where we typically take the galactic value, which is also empirically inferred. So I think we need to look into real plasma physics theory more to constrain this better and sort of get rid of some of these free parameters in these models. So thanks a lot. So this treatment is basically a great treatment in a sense. We are not able here to simulate a full spectrum of cosmic rays in this particular generation of the model. We are working on this to have a multi-energy representation. I mean, for us, most important are, however, the relatively low energy cosmic rays, the protons, which are carrying most of the pressure here. So the full spectrum, the more energetic ones are relatively unimportant for us.
I would also say that the transport of cosmic ray and the coupling depends on the alpha and Mach number of turbulence, because turbulence suppresses the streaming stability, and therefore it allows cosmic rays propagate faster. And if we have low alpha and Mach number, we have more chances for streaming stability to couple these fields.
Yeah, I agree with this comment, definitely. I mean, it's as I said, I think the properties of the turbulence need to be well resolved and well modeled, and also the plasma physics itself, the streaming instability itself is hellishly complicated. And we don't even, I mean, we're now working on real cosmic ray streaming, which we haven't even done here yet. And I think there's much need. I think this physics is clearly very interesting, and I find it that there's now a new connection between galaxy formation, possibly, plus high energy physics, where traditionally these processes have been examined.
We should talk more because I have analytical expressions of
Yeah.
this couple.
Yeah. Yeah.
Do you have your? Is this? Okay. Thank you.
Yeah, this should work. You have a new one. You have a USB-C.
Oh no, this is the older one.
This is the old one.
Yes. Sorry, guys.
You need the right adapter this time.
This one, that one. All right. Sorry, folks. I was having technical difficulties with my own laptop. It's one of the new USB-C connectors. I've never gotten it to work. All right.
Laura, do you have your microphone on?
Yes. I think I need a password.
I'm sorry.
Thank you. Thank you. All right. Awesome. Thanks. Okay. Can everybody hear me? Yes. Okay. All right. So I have a feeling that many of you guys came for the cosmology today, but I hope to hold your attention for just a few minutes about exoplanets and one planet in particular, which is a roughly Neptune-sized planet called WASP 107b. This is my new favorite planet, though I admit that my allegiances are somewhat fickle because every time I write a new paper about a planet, it becomes my favorite. So just a few details about this particular system. It was discovered by the WASP survey last year, the Wide Angle Search for Planets, which is a ground-based transit survey. And this planet is fairly unusual for a number of reasons. It's roughly 2 times the mass of Neptune. Planets in this mass range are fairly rare. It's unclear what would cause them to stunt their growth at that size and not become a Jupiter-sized planet. Another strange thing about this particular one is that its radius is larger than expected for its mass. Even though it's close to Neptune in mass, it's much more comparable to Jupiter in radius. It's fairly cool, equilibrium temperature below 800 Kelvin, which has important consequences for the atmospheric chemistry that I'll talk about in a minute. And excitingly, it orbits a very nearby, fairly small host star, which makes it a fantastic target for atmosphere characterization. So just to put it in perspective here, this is the expected size of the signal normalized to the best case for transmission spectroscopy. And the idea behind this technique is that when the planet transits in front of its host star, some of the starlight will filter through the atmosphere and can get absorbed there, resulting in spectral features that we can observe to back out the atmospheric composition. And so WASP 107b is highlighted in yellow here, and you can see that it's comparable to the best case planets that have ever been discovered. This is the best target that's been found in the last decade, which is exciting in and of itself, but it also is special because it's a much lower mass object, about 1/10 of a Jupiter mass, and much cooler equilibrium temperature, which allows us to study the metallicity and carbon to oxygen ratio of a planet in a very new regime of mass and temperature. So I jumped on this right when it was discovered. It I think everyone wrote an observing proposal like the day the paper came out. Unfortunately, mine got in there first. And so we studied the composition of WASP 107b's atmosphere in two different ways. One was to do interior structure modeling to reproduce the observed mass and radius. And the other thing we did was transmission spectroscopy with Hubble with C3. So the first thing was I call this planet the too good to be true planet because its atmosphere is so puffy. When it was first discovered, we all asked, can this thing actually exist? How can it be actually bound? And so Daniel Thorngren, who's a grad student at UC Santa Cruz, looked at interior structure models for the planet to say, okay, given its mass, how much, what mass of the core can we have, and what fraction of metals in the envelope can we have to reproduce the observed metallicity, or to reproduce the observed mass and radius. And so there's some uncertainty about the age of the system. If it's young, that helps the planet stay puffed up since it's hot. But even for the most conservative case of a very young planet with no core at all, we still put an upper limit on the atmospheric metallicity of 30 times solar. And so this is interesting when you compare it to the atmospheric metallicity trend seen in the solar system. We see that as planet mass goes down, atmospheric metallicity tends to go up because the smaller your planet is, the easier it is to pollute with planetesimal impacts as it forms. But our upper limit for WASP 107b falls just below this solar system trend, and so this is an interesting hint at a diversity of compositions for planets in this mass range. Okay, so we also, in addition to this, observed a single transit with the Wide Field Camera 3 instrument on Hubble, which provides spectroscopy between 1 and 2 microns. And this wavelength range, we're sensitive to features from water and also features from methane. So here's what the spectrum looks like. This is transit depth as a function of wavelength. This is backwards from what you would usually think of for a spectrum. Absorption is up because the planet radius is larger when the atmosphere is more opaque. And so we did a retrieval analysis where we basically varied the atmospheric properties to see what range of climate and composition is allowed to fit the observed spectrum. And we see that water is required, so that big bump at 1.4 microns corresponds to a water bandhead. And so that was expected. We think that as planetesimals fall in, they'll mainly be icy, and so that will give you a lot of water in your atmosphere. The thing that we didn't expect is that we did not see any evidence for methane, and that constrains the ratio of carbon to oxygen to be fairly low, lower than the solar value at about 2.7 sigma confidence. This is interesting because we think that it could suggest that maybe there's more planetesimals falling in, more water ice relative to other species. And I hope that this will be confirmed by future high-precision observations over a wider wavelength range. We also see evidence for thick condensates at high altitude. So even though that's a very, very confident detection of spectral features, they're much lower in amplitude than we expected for a cloud-free composition. And so we put in an opaque gray cloud deck in our model, which we constrained to be present at an altitude of about a millibar, which is much, much higher altitude than the clouds that we see in the solar system. So just to put this in context a little bit, this is the first system where we actually have, this is the lowest upper bound that has ever been measured for C to O for a transiting planet. On the left, I'm showing constraints for some transiting hot Jupiters. The yellow line is solar C to O. You can see that C to O is typically constrained to be less than 1 at 3 sigma confidence. But our result for WASP 107b constrains C to O to be less than about 0.6. And the reason we're able to do this is that at these lower temperatures, the dominant carrier of carbon is methane, which is something we're sensitive to in our observations. Also, to put the condensate properties in context, Caroline Morley, who's a Sagan Fellow here at the CFA, ran a couple of physically motivated cloud and haze models to see what kinds of aerosol properties give us the best match to the data. And these 2D histograms are for another planet of similar temperature, also low mass, that has very high altitude clouds in its atmosphere. And then the blue stars correspond to what we found gives a pretty good fit for our observations of WASP 107b. And so we're seeing that assuming on the left it's an equilibrium cloud for varying atmospheric metallicity and cloud sedimentation efficiency, that is to say how easily the cloud will condense out of the atmosphere. And we're finding that we can have lower metallicities and less lofted clouds for this case than was possible for GJ1214b, which we're comparing to. And on the right, I'm showing haze models with varying particle size and haze production efficiencies. That is to say, these hazes are photochemical in nature, and with methane as a precursor. And so UV photons come in, break up the methane, and then it recombines into thick hazes. And so we're finding that for this planet, smaller particle sizes and slightly lower haze production efficiencies give us a good fit to the observed spectrum. So this is showing that we have a diversity of cloud properties for these small, cool planets. Okay, so just to wrap up, WASP 107b is totally the best exoplanet until I publish another paper, and then I'll change my mind. For realistic assumptions about the atmosphere and about the planet, namely that it has a 5 Earth mass core, we constrain the atmospheric metallicity to be about 20 times solar, which is much lower than we would expect based on the trends seen in the solar system. We also see a possible subsolar C to O ratio, which suggests maybe that there are water-rich planetesimals falling in and polluting the atmosphere of the planet as it forms. We also see evidence for thick clouds that can be reproduced with physical models that are different than for other planets where we've observed clouds as well. And finally, I'll just say that there's a lot more to come for this planet. This is just a first crack at what its atmosphere is like. But observations of it have been included by all 4 of the GTO teams for JWST observations. So there should be more on this coming soon. All right, thank you.
Most excited about things that have a white load.
But best is a subjective, I'll change my mind next week.
Questions for Laura?
Laura, is the fact that your clouds are thicker or denser, does it constrain the amount of galactic cosmic rays that ionize?
Oh, that's a good question. So we think that the cloud formation, so clouds could just condense in chemical equilibrium, or you could produce photochemical hazes, but we think the mechanism for that is actually UV radiation from the host star, not galactic cosmic rays.
So you may have said this actually, but when you model clouds, do you have a uniform cloudy material, or do you have clouds with gaps?
Oh yeah, that's a good question. So our best fit model was a global cloud with gray opacity. We've thought a lot about patchy clouds, and the data show no evidence for them, but there would be a spectral signature of that if it existed, yeah.
So my problem is how to keep you beyond the official time. And I decided to say that I'm going to talk about dark matter. And I will explain you why. Because why we introduced dark matter? To reconcile theory and observations. There is another very well-known way to reconcile theory and observations. If something does not make sense in astrophysics, appeal to magnetic fields. And if it still does not make sense, say that they are turbulent. So my work is on turbulent magnetic fields. this is my host. And I am going to, advertise some talks that I'm going to give tomorrow in 3 groups. So I have 3 hours talking. And, we live in a turbulent world. You wouldn't mention, we would not question this, but this turbulence helps us. This is the challenge of Van Gogh, the Hubble postdoc in Madison made. She challenges this Starry Night by Van Gogh, and she said, this is with turbulence, but I can do this without turbulence. This is her drawing. Well, turbulence helps us, in fact, because we don't need to wait 4 months for coffee to get sweet. This is what you can calculate using molecular diffusion. We just use spoon and create turbulence. But turbulence, in fact, is very important for many processes. And these are some of the processes that I worked on. I surely cannot cover them all. But I will be talking about some of them during one of my talk. And this is how turbulence changes the reconnection rate, the ability of magnetic fluxes to change their topology. These are 2 eddies, and these are magnetic flux tubes. They are interacting and changing topology, introducing an effect which is orders of magnitude stronger than the ambipolar diffusion in molecular clouds. And these are simulations of accretion disks with this effect, which allow to solve, for example, the breaking catastrophe for circumstellar disks. So my talk and Lars Helqvist's group will be the most basic. I will discuss the properties of MHD turbulence and implications. The most important will be gross violation of flux freezing in realistic turbulent media. And we have now both numerical and observational evidence for that. Well, when we are dealing with any observations of cosmological nature, and I believe the observations that we're all discussed today is not the exception. We have to look through a screen, but this screen is turbulent, and this screen changes a lot. We need to, for example, to measure this E and B modes in cosmology go 100 times lower than the level of fluctuation arising from turbulence. And this is, makes us think hard how to make sure that we understand what is between us and our object of desire. We want to not use it as a black box. We want to know statistical properties of it. And recently there was a paper by this well-known authors who said that the analysis of Planck data contradicts to what we know about turbulence. Recently, and I will be discussing this at John Kovac meeting, and this will be at this time, tomorrow. We analyzed this data and found the constraints of the turbulence. So we claim that it's the modern understanding of turbulence is adequate, MHD turbulence. But there are these constraints. And this brings us to another problem, how to study magnetic fields, how to study characteristics of turbulence. And this is what I will be discussing at Avi Loeb's group. And this is related to velocity gradients. These are simulations of MHD turbulence, and these are isocontours of equal velocity. And you see that these isocontours are elongated along magnetic fields. Therefore, we have a new technique to measure magnetic fields. We can just measure this, how magnetic velocity is changing across these filaments, magnetic velocity filaments, and we know the direction of magnetic field. And this is an illustration of how efficient this technique is. These are polarization by Planck, and this is Galfa H1 data, velocity gradient. These textures in both cases correspond to magnetic field. This is diffuse data. This is molecular cloud data. Again, textures correspond to molecular magnetic fields, and for polarization, this is blast pole data, this is CO data. We have a very good correspondence. Initially, we were working only on this 2D gradients, and this is Galfa data against Planck data. You see red is velocity gradients, yellow magnetic fields. But now we are using all the three characteristics of gradients. One is the direction of gradients. This is shown. We can use gradient amplitude, and we can gradient distribution function. And this gives us, this is traces direction magnetic field, this gives sonic Mach number, this gives magnetization, Alfvénic Mach number. Combining this, we can find three-dimensional distribution of magnetic field, shocks, and identify the regions of gravitational collapse. For example, we can use velocity channel gradients and find the distribution, a three-dimensional distribution of magnetic fields in, for example, H1 or in molecular clouds. We've done this, but how to test this? We can test this. We can use starlight polarization. And this is the result of the starlight polarization. This is our location, this is the center of the galaxy. And for some stars, we know both distances and we know also polarization. So with our map, we predicted the polarization we expect, and we compared. This is the alignment measure. Black corresponds to essentially perfect correspondence between polarization and our predictions. We can study with this technique something that we cannot study anywhere, any other ways. For example, this is the textures correspond to magnetic field of high velocity clouds. They have very low the column density, so you cannot do this with polarization, but we can do this with the technique. So we can find the magnetic field magnetization, Alfvén Mach number. Alfvén Mach number is the ratio of the turbulent velocity to Alfvén velocity. And with this distribution of gradients, we can find, this is the map, again, with Galfa data. And this is galactic plane regions where we have larger Alfvén Mach number, which means that we can have super-Alfvénic turbulence. And we see that when we go to low, high altitudes, we have subalfvénic turbulence. By the way, this is very much related to what we heard just a couple of minutes ago about the coupling between cosmic rays and matter. Because this cosmic rays and matter does depend on, coupling depends on the Alfvén Mach number. This is sonic Mach number, which is defined this way with also for galactic plane. Interestingly enough, shocks are perpendicular mostly to magnetic fields, and this results in a possibility of measuring shocks. These are places where there's green lines corresponding to density gradients are perpendicular to velocity gradients corresponds to shocks. Well, we study many other regions. We can identify self-gravitational regions because of changes of properties of velocity gradients. I don't have time to discuss this. This is application of this technique. Moreover, we can use not only velocity gradients, we can use other gradients, synchrotron intensity, not polarization. We can use, and this is correspondence between the synchrotron intensity gradients and synchrotron polarization for the data by Planck. So, the importance is that there is no necessity to correct for Faraday rotation for this technique. We can get the right directions without it. But if we use polarization, we can get even more. We can get tomography of magnetic field. This is we've done only with numerical simulations. This is the 3D distribution of magnetic fields that we restore from our numerical simulation. This is synthetic so far data. This is red vectors restored with the technique. And this is a slice, three-dimensional slice of our data with magnetic fields, which we know, and with synchrotron polarization gradients. I'm happy to discuss more with you, and therefore I'm giving you my email address. So thank you.
So in molecular clouds, regions of shocks can also be regions where you have gravitational collapse that's starting. So can the technique distinguish those?
Yes, because I didn't have time, but as I said, there are different types of gradients, and velocity gradients and density gradients or intensity gradients behave differently. So velocity gradients are not sensitive essentially to shocks. Therefore, we can distinguish by combining.
Another one too, yeah. Oh, I think that pointer may also. Oh no, pointer's not very
I also next week.